Hello and welcome everybody to NCI Presents TechTake. My name is Benjamin Joecker and I'm from the Center for Quantum Computation and Quantum Communication Technologies at the University of New South Wales in Sydney. And today I would like to talk about efficient models for the design of a donor-based quantum computer in silicon. I would like to start my talk with the words of Richard Feynman. Nature isn't classical, damn it. And if you want to make a simulation of nature, you would better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. So what Richard Feynman realized is how difficult it is to simulate a quantum system. And he proposed to build a machine that directly processes information directly in the way that the quantum world works. And throughout my talk, you'll see how much effort I went to just simulate a very small quantum system. And in that sense, my talk is a perfect motivation to why we need a quantum computer. Let's first try to understand how classical information is different from quantum information. So in a classical computer, we encode our informations in bits, so zeros and ones. For instance, a 3 in binary is 0, 0, 1, 1. And a classical computer can use this encoding to compute that 3 times 5 is 15, which in binary is 1, 1, 1, 1. Physically, this information is implemented as the voltage drop over a transistor, where low voltage is a 0 and the high voltage is a 1. In a quantum computer, we encode our information in an atom or in the state of an atom. Specifically in our computer, we use the spin of an electron. You can kind of imagine the spin as the needle of a compass, which can either point along the magnetic field, which is our 1 state, or in the other direction, which is a 0 state. And what's really special about the quantum world is that it can also be in a superposition state. And you could kind of say that it's both at the same time, so 0 and 1. Additionally, the state of a qubit can be inseparably intertwined with the state of another. We call this entanglement, and here's an entangled state. An entanglement is really something that broke Einstein's mind. He didn't want to believe in it, and he tried to come up with experiments to prove that quantum theory and entanglement isn't real. And funnily enough, these experiments in the end, when technology was advanced and we could actually do them, could be used to show that quantum theory is indeed real. So now let's look at the information density that 3 classical bits have compared to 3 qubits. So 3 classical bits are just 3 numbers, 3 zeros or ones, so just 3 bits of information. But to describe 3 qubits, so the state of 3 qubits, what you need are 8 complex numbers. And in general, to describe n qubits, you need 2 to the n complex numbers. So this grows exponentially. And for just 53 qubits, you already need 10 to the 16 complex numbers. And I didn't choose this number by accident. In 2019, Google showed that their 53 qubit processor could perform calculations that you couldn't run on any classical supercomputer. So no classical computer can deal with this large number of complex numbers very easily, but quantum computer can. So now we are really interested in how we can manipulate quantum information or classical information. So classically, we can just take the state of a bit and flip it. That's the NOT operation. So 0 becomes a 1 and a 1 becomes a 0. The quantum equivalent of this is an X operation, where again, the 0 state becomes a 1 state and the 1 state becomes a 0 state. But if you apply this X operation on the superposition state, you can see that if you flip both parts of it, you end up with the same state. So this really already shows how different quantum information is from classical information. Additionally, I really want to, in particular, talk about 2-qubit operations today. And here I show the example of a swap gate, which swaps the states of 2 qubits. So the 0, 1 state becomes the 1, 0 state. And again, if you now apply the swap gate to an entangled state, so swap the 2 states of the 2 qubits on both of these parts, you can see that you again end up with the same state. So this is quite different from how classical information processing works. So to physically implement these qubits, in our labs at UNSW, we use phosphorus donors in silicon. So compared to the silicon host crystal, the phosphorus donors has a net positive charge and can bind an electron, which is negatively charged. Then the qubit is implemented in the spin of our electron, which in the externally applied magnetic field will split energetically into the down and up state. Just like the electron, the phosphorus donor also has a spin, which can either point along or perpendicular to the magnetic field. And if it points perpendicular, anti-parallel to the magnetic field, it will act as an additional, as a magnetic field that reduces the strength of the external magnetic field and reduces splitting of the two spin states. So in our labs, we would have a chip like this, where here in the center region, we would have our donors implanted. Then we have some electrostatic gates here in purple to tune our system. And in green, we have a single electron transistor, which we can use for readout. We apply the magnetic field along this blue arrow here. And now to do the 1-qubit operations, we use this microwave antenna here. So what we do here is a technique that is very similar to what you would know under MRI. So if you've ever been so unfortunate that you had to go to a hospital and put yourself in an MRI machine, what the MRI machine did to the nuclei in your body is very similar to what we do to the electrons in our chip here. Just we don't call it MRI, we call it electron spin resonance. So what we do is we use this microwave antenna to apply resonant magnetic driving fields that can drive transitions between the up and down state. So here we apply the pulse and then drive transitions between the electron states. And here is a measurement from our lab where we show the spin up fraction as a function of driving time. You can see that we go from an up state to a down state periodically. And actually in between these two extreme cases, we have something that we identified as a speciality of quantum theory before, which is a superposition state. Now to do 2-qubit operations, we obviously need 2 donors. So here we have 2 donors. For one, the nuclear spin points down, for one up. And these are the energy levels. So you can see here for the right donor, the splitting is a little bit bigger because the nuclei points along the magnetic field, while here it's a little bit smaller because the nuclei is anti-parallel. The combined energy levels of these 2 qubits are then given here on the right, where the splitting between the anti-parallel spin states is just given by the difference in magnetic fields through these nuclei. Now, as we bring these 2 donors together, the electrons will start to interact. And this interaction is called the exchange interaction. It's called exchange interaction because it has the effect that it tries to exchange the spins of the 2 qubits. So we get something that are called the exchange oscillations, where we get transitions between the down-up state and the up-down state. And again, in the middle between those 2 extreme cases, we get something that we before identified as an entangled state. So the thing that Einstein really didn't believe should exist. So this exchange interaction is something really intuitively useful to implement a swap gate, because in the swap gate we exchange the spin of 2 qubits, and this is exactly what the exchange interaction does. So we start off at a value of exchange that is very small, so that we can nicely implement our states without having any rotations. Then we electrically detune the system, which ramps up our exchange interaction. How this really works, I'll explain in a minute later. Then we get these exchange oscillations. And if we just stop after half a cycle, we exchange the spins and quickly go back to switching off the exchange interaction and perform the swap gate. Just because I'll use it later, I would like to explain one more way to perform a 2-qubit gate, which is to perform an X gate on the right electron conditional on the state of the left. So if we go to a very small exchange value, so smaller than 10 megahertz, All this does is it slightly hybridizes the anti-parallel spin states, but crucially, it changes the resonance between the green and the red transitions. So if we now apply a driving field that's resonant with the green transition frequency, we can flip the state of the second electron if the state of the first electron is down, while if the state of the first electron is up, the state of the second electron remains unchanged. Yes. So the question I try to now answer with my simulations is, how do we need to position the two donors in the crystal to achieve the right couplings? What uncertainties can we tolerate? And what fields do we need for the tuning? And if you look at the picture of these two electrons and the two phosphorus donors in the crystal, you can see that these electrons will interact with thousands of atoms. And to simulate this whole quantum system, we either need a good quantum computer, which doesn't exist yet, or we need some efficient models. To model the donor electron wave function, we have a few options. There's density functional theory, which unfortunately is computationally very heavy, but it doesn't rely on any fitting parameters. So it's also called ab initio method. Then there is time binding, which is more affordable, but not free of any fitting parameters. And then there is the multi-valley effective math theory, which I used here, which is comparably quite inexpensive. It's quite intuitive, but it does depend on empirical fitting parameters. Effective math theory was developed in the 1950s, where people started to really get interested in donors. And for instance, they measured these absorption spectra. And what they saw is that the orbital structure of the phosphorus donor in silicon is really not too different from that of a hydrogen atom. They thought maybe we can describe the state of these phosphorus donors by something that's very similar to a hydrogen atom in vacuum. So they used this effective hydrogen-like equation where they gave the motion a kinetic term that has a mass, it's an effective mass, so the effective crystal mass, instead of the mass of an electron in vacuum. And instead of the Coulomb potential of the proton and the electron in vacuum, they gave the crystal electron the Coulomb potential of an electron in the silicon dielectric. And this theory was really quite successful in predicting these main orbitals of the phosphorus donor. But unfortunately, silicon is a little bit more difficult. So silicon is an indirect semiconductor, which means that it has 6 valleys. So these 6 valleys, which are degenerate, belong to the 6 principal crystal orientations, shown here at the top. Then a donor potential breaks the symmetry, so breaks the degeneracy of 6 valleys, so it couples these valleys, and then splits the energy of the 6-fold degenerate 1s manifold. And we get these energy levels here on the right, where the ground state, A1, is plotted here at the top. So what we want to calculate here is the exchange interaction. And here I compare different attempts of using effective math theory to calculate this in history. And what you can see is that really the shape and the order of magnitude over all of these calculations really differ between different approaches. And here I would like you to understand how this is different. So first, all these methods differed in how they treated the valleys, so how they could compute these valley orbit coupling. Here we used Bloch functions, so the crystal functions computed with density functional theory, and they were well converged, and this is quite accurate. Secondly, we really need to find a good impurity potential. So this approximation that the electron sees 1/r Coulomb potential of in the dielectric is really only valid for when the electron is very far away from the donor. In the central region, so in the central cell, this donor will disturb the local charge environment, and we need some corrections. In this work, we used the tetrahedral central cell correction, which fits ab initio calculations that found a similar shape. Thirdly, you need to pick a method you use to evaluate the electron correlation. So you need to find a method that takes account how two electrons interact with each other. Here we use something called full configuration interaction, which is the best possible solution within a given basis set. And the choice of the basis set is the last crucial point, and I would really like to talk about this more in this talk. So when you pick a basis, you really want a basis that directly describes the state or directly reproduces your final solution. And for a hydrogen atom, this is a Slater type orbital, so e to the minus alpha r, where alpha is a decay constant. And we would expect something very similar for our donor states. But here we have one crucial difference, namely that in these valleys, the motion along the valley has a different effective mass than the motion perpendicular to the valley. So this means that we expect our electrons to be much more confined in the direction along the valley than the direction perpendicular. And what we need are anisotropic Slater type orbitals, an orbital like here, where you have a different decay constant along the valley than perpendicular to the valley. From a computational point of view, what we would like to use are anisotropic Gaussian orbitals, which look like this, because we really came up with a really neat trick to compute our Coulomb kernels. So what we need to calculate to solve our donor states are the integrals over our basis function times the 1 over r potential. And what we did here is we decomposed our 1 over r potential in a Gaussian quadrature, and this allows us to split up these integrals in separable integrals over just Gaussian functions, which can be solved analytically. To really use the advantage of having an orbital where you need very little basis functions, because it fits the final solution already quite well, to having analytic solutions for your integrals in the Gaussian type orbitals. To get the best of both of these worlds, we did something called STONG. So we fitted a number of Gaussian type orbitals to a Slater type orbital. And here you can see that these three Gaussian type orbitals quite nicely reproduce the one Slater type orbital. So we now had our type of basis. So we were wondering what size do we need, and we trialed a small basis set as well first up, where we only use 3 basis functions. And we found that it was impossible to match the energy of the E valley states and T2 valley states at the same time. Secondly, we tried a larger basis set where we also used 2s-like orbitals, so orbitals with like x squared, y squared, or z squared here, and found that there it was indeed possible to fit all valley states at the same time. So what we really want to use these basis sets for is to compute the exchange. So the splitting between the 2 lowest energy states, which belong to the orbitals of the entangled spin states of the singlet and the triplet. So I plotted the singlet, triplet, and their exchange interaction, the difference between both basis sets here as a function of donor separation along 3 different crystal orientations. And you can see that for short distances, the fine features of the basis really matter, and you get strong differences. But for the larger distances, above 10 nanometers that we are interested in, it really doesn't matter if you use the small or the large basis set. And we concluded that you can use the small basis sets for our computation, which are much cheaper. Here I plotted both basis sets, the exchange value as on a logarithmic scale as a function of distance for the same 3 crystal orientations. And the large basis set is shown in the full colors and the small basis set as a grayscale behind. And what you can see, here's the same plot where I just plotted the difference between these 2 sets as a function of the exchange interaction itself. But you can see that it's really hard to predict small exchange values. But this is a natural effect and will happen in any type of simulation. And it's much more advantageous to use the efficient small basis sets, where all these calculations only took 600 service units, compared to the large basis sets, where these the computations shown here took 16,000 service units. So now let's see how we can use these results to design the position of our donors for conditional rotation 2-qubit operations. So for high fidelity, we wanted to have an exchange value between 0.1 megahertz and 10 megahertz. So this range is shown here by the dotted lines in the exchange interaction, which is shown as a function of distance on a logarithmic scale for the 3 crystal orientations. And you can see that for high fidelity operations, we have to position the donors between 10 and like 24 nanometers in distance. And you can also see that there are really large distance differences between the 3 crystal orientations. And to understand this better, I plotted the electron wave functions for you. So here is the ground state, the singlet, the first excited state, the triplet, and here at the bottom is their difference, which in the end causes the exchange interaction. And here you can see how they change as the second donor is moved away from the first. I would like to point out a few things here for you. First, you can see that for short distances, the triplet is quite different from the singlet. This is due to an avoided crossing with the first excited valley states. And secondly, you can see that the difference between these two states is quite significant, which leads to really high exchange interaction for this orientation in the crystal. If we now go along the 110 crystal orientation, so here, which belongs to these yellow results here, you can see a few differences. Namely, as we go diagonally in space, you can see how we get interference effects between these two donors. So through the structure of the crystal electrons, so the Bloch functions, we get jumps here, which leads to these energy oscillations, which we call the Valley oscillations. Finally, if we go along the 111 direction, so here I had to plot a different cut plane, because now we go really across the unit cell. So I cutted this cut plane here shown in gray. And the structure looks quite different because we have a different cut plane now. You can see one more interesting feature, namely that the wave function of the second donor seems to periodically flip. This is due to the nearest neighbor configurations of the second donor. So here the first donor has the nearest neighbor bonding orbitals down, and the second one up here would have it up. So it periodically flips in nearest neighbor configuration, which flips the second state. And additionally, this the difference decays quite quickly, which then leads to a small exchange value. So far I only shown to you the exchange interaction as a function of distance, but when we implant our donors, we also might have angular uncertainties or angular effects. So to really look into that, I did these 3D iterations where I positioned one donor in the center of a sphere and then the second one at a lattice site the closest to the surface of the sphere. And I went from 5 to 50 nanometers. And you can see that the exchange interaction really shows these features described above. It's really strong along the principal crystal axis and then really weak if we go across. But you can also see that the exchange interaction really varies by orders of magnitude for just small changes in crystal direction. And I was wondering, is this really detrimental to our approach of building a quantum computer? So to check this, I performed a spot check. I positioned one donor at the origin and the second 19.5 nanometers away from that. It's a configuration that's viable for high fidelity CROT gates. And then I varied the position of the second donor, so the one away from the origin, in a sphere around its original position of 1, 2, and 3 nanometers, and calculated the corresponding exchange values and put them in the histogram here. And you can see that even for the 3 nanometers sphere, still 60% of donor positions give you a viable exchange value. And additionally, here you can see that most of the deviations are for values smaller than the desired exchange. And there you can use electric fields to detune the exchange, the donor system, and increase the exchange and get those values back into the desired region. So to close, I would like to show you how to do swap gates, where we need to understand how this detuning and the increase of the exchange interaction works. So here you can see the exchange interaction as a function of detuning for two donors positioned along the 100 crystal direction, where we positioned the where the largest value here is for two donors with a distance of 10 nanometers, while the smallest value is for two donors with a distance of 25 nanometers. And you can see that for zero detuning, this is just the exponential decay we saw in the plots as before. Now, as we increase the detuning, we'll get more and more contributions to the electron states, where both electrons are positioned on the same donor. So they are very close together and really strongly interact, which increases our exchange interaction. This gives you stronger and stronger exchange values until we go to the point where actually the second donor is so far down that both electrons are completely positioned on the same donor, have the strongest possible interaction, and our exchange interaction here is saturated. So now to perform a swap gate, we wanted to be able to tune our exchange interaction from the value that's small compared to the magnetic field given by the anti-parallel nuclear spins. So from this value here, where we pick two donors positioned 90 nanometers apart from each other, then we want to go to a value where the exchange is large. So we get exchange oscillations like this, and then quickly tune it back. And we performed the swap gate. And to close, I would like to show you one more thing. So here are the same evaluations for two donors positioned along the 110 crystal direction, again from distances 10 to 25 nanometers. And the only real difference you can see here is that as the two donors move away from each other, we don't get a linear, exponential decay, but we can see these valley oscillations, so the discrete jumps of the exchange interaction. So one more thing, even if the nuclear spins are parallel, we'll still get small deviations from donor to donor in the magnetic fields they give to the electron. So we can do the same protocol also if the nuclear spins are parallel. We just have to do everything at smaller exchange values because the exchange now again needs to be small compared to this difference. And again, we go from now smaller exchange values that's smaller to the magnetic field given by the nuclear spins to a value where the exchange interaction is switched on, and going back to a value where it's switched off, and we performed a swap gate. With this, I would like to close and point you into the direction of my paper where I describe this all in much more detail. Thank you for listening.